Welcome to The Explainer, everyone. Today, we are taking all those hours you've spent staring at your structural steel design coursework and bringing them right into the real world. We're going to perform a forensic autopsy on a massive structural failure, using the Indian Standard 800-2007 code as our absolute detective's manual. We want to uncover exactly why a brand new bridge suffered a totally catastrophic collapse. Get ready, because you're about to see the forces you calculate on paper come to life. And honestly, the consequences are devastating. Picture this. You have a 60-meter, 160-ton steel truss bridge. It is completely finished, just sitting there waiting for its grand opening. And then, under its own weight, it violently buckles and sinks over 2.5 feet. How does that even happen? Well, this is the true story of the Lamgadi Bridge in Nepal. It was supposed to be a pilot project, a slick, economical propped cantilever steel truss to cross deep river gorges. Instead, it turned into a terrifying lesson in structural mechanics. I really want you guys to think like forensic engineers as we break this whole thing down. Okay, let's dive into our investigation roadmap. We're going to hit the collapse timeline, IS 800 limit states, the fatal support error, shear and connection failures, member buckling, and wrap it all up with the critical lessons for steel design.
All right, Section 1, the collapse timeline, the fall of Lamgadi.
So, the bridge was fully erected using temporary timber supports underneath the trusses, right? The concrete deck is poured, and by day 43, it's totally hardened. Day 44, morning time, the crew starts knocking out those temporary supports so the bridge can finally hold its own dead load. They get the propped end out fine, but on the fixed end, the timber blocks are jammed tight. The forces are clearly already doing something weird. So the workers actually set fire to the blocks to shrink them and then hammered them out. And that is exactly when a massive, terrifying noise echoed across the gorge. A top cord of the truss had locally buckled. Over the next few days, it just got worse. Tearing noises continued as this huge structure sank an unbelievable 801 millimeters. That's over 2.5 feet. It was literally crushing its own foundation walls.
Moving on to Section 2, IS 800 limit states. This is where theory meets reality.
You guys know IS 800-2007. The limit state of strength is all about preventing loss of equilibrium, loss of stability, and rupture. Well, Lamgadi completely failed on all fronts. Equilibrium, gone. The localized buckling was a textbook loss of structural stability. And the tearing of the steel connections, pure rupture. And remember, this wasn't from a massive storm or an overloaded truck. This happened purely under the worst possible combination of its own dead weight.
And of course, before a structure ruptures, we always check the limit state of serviceability, right? Making sure it doesn't sag or vibrate so much that people can't use it. The Lamgadi Bridge was designed to deflect maybe 43 millimeters max under its dead load. Instead, it sank 801 millimeters. The serviceability was absolutely obliterated before the ultimate strength even fully gave out. So you gotta ask, why did it deflect so drastically? Let's figure it out.
Which brings us to Section 3, the fatal support error, a simple swap, a catastrophic result.
Now, Lamgadi wasn't just your standard, simply supported beam where maybe mixing up a hinge and a roller isn't the end of the world. It was a propped cantilever system. These rely on a very specific support arrangement to manage force distribution, especially lateral forces and thermal expansion. The support placement is incredibly sensitive. The blueprints clearly called for fixed hinge supports at one end and roller supports at the propped end so the bridge could naturally move longitudinally.
Now, what's really interesting about this slide is the deadly contrast here. Look at case A, the design. Roller at support B1, hinge at A2. Makes perfect sense. Now look at case B, the site reality. The installation crew literally swapped them. They put the hinge at the propped end and the roller at the fixed end. It seems like such a simple mix-up, but it structurally locked the entire bridge into a completely unnatural load path.
Section 4, shear and connection failures, when forces have nowhere to go.
3,215 kilonewtons. Because those bearings were backwards, all those massive compressive forces suddenly couldn't resolve into the ground. They were trapped. So the rigid concrete deck and the flexible steel truss basically went to war with each other. This dumped a shocking 3,215 kilonewtons of unexpected shear force directly into the crossbeam at grid L. That is a force it was absolutely never, ever designed to carry.
Let's walk to the domino effect on these joints. Step 1, the temporary supports get hammered out and the dead load crashes onto those swapped bearings. Step 2, the locked-in forces make the steel truss try to physically slide underneath that heavy concrete deck. Step 3, the top crossbeams, stuck in the middle of this massive structural tug-of-war, suffer extreme shear deformation. We're talking sliding up to 86 millimeters. And Step 4, the cleat angles just fail.
Now, in IS 800 design, we want our connections to be ductile, right? We want them to yield gracefully and give us a warning. But this trapped shear force was so aggressive that the connections suffered catastrophic brittle tearing. The shear connectors were just ripped apart.
Let's move to Section 5 and see how this builds. Member buckling, the final straw.
Okay, so the shear connections are totally tearing. That means the massive compressive load has to quickly redistribute through the top chords of the steel trusses. But remember, the fundamental structural geometry is flawed. This causes insane overstressing. The left truss top chord at panel 8 and the middle and right truss top chords at panel 9 went into excessive buckling. When engineers checked the design against IS 800, the compression ratio on these members blew way past the strict 1.0 safety limit. The steel members were literally being crushed by the bridge's own locked-in forces.
And this is exactly how physical damage maps straight back to your textbook definitions of instability. These top chords were built-up channel sections, really heavy steel plates laced together. But under this immense, trapped compressive force, the flanges and webs experienced severe local instability. They crippled. It's the exact local buckling behavior you study when you're looking at slenderness ratios. The steel literally folded like an accordion because it was handling a load it was never supposed to see.
Which brings us to Section 6, Lessons for Steel Design. Execution dictates survival.
So, what are the big takeaways for us here? First, workmanship matters absolutely. The forensic guys found poorly tightened bolts, entirely missing bolts, and eccentric bracing connections all over the place. While that didn't directly start the collapse, it completely compromised the structure's ability to survive it. Second, force redistribution is real. When those cleat angles yielded and tore, the forces didn't just vanish. They violently forced a new equilibrium path straight into the top chords, causing them to buckle. And third, the domino effect. A simple, careless bearing installation error down at the foundation completely destroyed a 160-ton superstructure up above. The load path is everything.
Let's actually look at the official summary from the engineering report. The damage occurred under self-weight of the bridge, mainly due to unintended displacement of the support. Guys, that is a really sobering reality check. You're going to spend hours calculating wind loads, seismic activity, moving vehicles. But if the fundamental support mechanism at the base is flawed, the structure's own dead weight is more than enough to tear the whole thing apart.
So, I'm going to leave you with this final vital thought. As you're grinding through your IS 800 codebook, calculating shear capacities and buckling limits, remember Lamgadi. When you sign off on your very first professional design, will you know exactly how the load reaches the ground? Because if you don't, or if your instructions aren't absolutely crystal clear to the crew out on site, nature's going to find its own load path. And trust me, it rarely chooses a kind one. Keep studying, keep asking questions, and never ever underestimate the power of a single support bearing.